Welcome to the next video in the systems programming video series. We're moving on in the textbook Dive into Systems to its section 4.7, talking about integer byte order. And this is really just a conversation about little-endianness versus big-endianness. So what's going on here is, everything we've talked about so far has primarily just been storing information in a single byte, if that really, but that realistically, the smallest address, right? Like you can only address bytes in memory on almost any computer. So everything we've talked about being located at basically a single address is, being located with the size of this, with memory the size of a byte, which is 8 bits. But we know that some data structures like ints are actually stored with more than one byte. Ints are, I think, typically 4 bytes. There is this thing called a short, which is 2 bytes. And ints are 4 bytes on most, hardware. So there may be some variation on this, but usually it's 4 bytes for an int. But anyway, let's just look at a short, which is 2 bytes. And let's think, well, okay, so I think maybe it makes more sense to look at a concrete example first. So let's actually look at this program. It's going to continue on to the next page. There's not much to see here. I mean, this is just like we're importing standard IO and we're declaring our main function. So the code is over here. And let's look at this example where we are storing a hexadecimal value. I haven't talked in much detail about hex values, so maybe now is the time. So a hex value, I have said before that you have the digits 0 through F, right? And there are 16 digits in total. F is the largest one, and it represents the number 15. This means that we can store 16 possible values with just a single digit. And that is 2 to the 4. So what that must mean is that in order to do this in binary, we need 4 places, right? So any given hex value, right? One hex digit requires 4 bits, right? So that you could store all of the 2 to the 4 possible values, hex digits. Now, since we tend to work in bytes and bytes are 8 bits, then that means that any one byte can store 2 hex values. And so that's kind of why in this example, to kind of keep things simple, we're writing these pairs of hex values. So in order to read this, think that the DD, that the very end, the rightmost end of this hexadecimal number, is a D, and that D sort of, because of the positional system, is the same as D times 16 to the 0, right? This is, again, the whole concept of like a base number system. Here we're using base 16. This D is D, and keep in mind, right, D is what? A is 10, B is 11, C is 12, D is 13. So this is like the same as 13 times 16 to the 0. And then because of how base or positional systems work, this next D is D times 16 to the 1. So that's what, 13 times 16. This C really means 16 times, C times 16 to the 2, and so on, right? So that's how to read this as a hexadecimal number in base 16. In order to store this, right, think this is an int value. Because it is an int value, it is made up of 4 bytes. And here you see the 4 bytes, right? 1, 2, 3, 4 bytes, each byte holding 2 hex values. So all of the space lines up, right? Everything is fitting within the allocated space. Now, what are we going to do? We are going to print this thing out at the byte level. So in order to allow us to read a single byte at a time, that is more or less what a char value allows you to do. So we are going to make a char pointer and give ourselves the control, the power to control where we're pointing one address at a time, right? Because a char takes up a single byte, And then if we have a pointer to that char and we increment that pointer, it will increment 1 byte at a time. So that's why we're declaring this the way we are. And it is going to point to the address in memory where value is stored. So we're getting to look at it 1 byte at a time. So that's exactly what this loop does, is it increments up to size of value. Size of value, notice, right? Value is a type int, and ints have 4 bytes. So the size of function is going to tell you how many bytes you need. So size of should evaluate to 4. So this for loop will execute 4 times with I ranging from 0 to 3. And what do we do on each iteration? We print the address, the value that we find at that address. We could talk about how to read this format string, especially up to here, but it's printing basically. It's doing the job of printing these hex values. Then we feed these values in. Okay. And then after we print, we increment p, recalling that because p is a char pointer, that means we increment by a single byte each time. So we get to look at each byte. And if you think about it, right? So like, what would you predict if you're trying to think about what, like if you print every byte, a natural thing to guess is that the first thing it's going to print is the first byte, which is AA. So that's what we're going to see on the first print. And then on the next print, it's going to print BB, CC, DD. That's maybe what you expect, and then what it prints is maybe not what you expect. It first prints out DD. Why would it do that, right? It doesn't DD come last. Well, this is the whole concept of a big-endian versus a little-endian memory system. So it doesn't matter what, right? I mean, as long as in the carved out space for value, as long as the computer knows how to read the sequence of digits, or the sequence of bytes, I guess, really, then as long as the computer knows how to manage this, it doesn't objectively matter whether it's written from least significant byte to most significant byte. But sometimes it matters for us as programmers, especially if we're trying to like debug things, or for whatever reason we're looking at things at the level of addresses in memory, at the level of bytes. So there's no right or wrong way to do this. You could write that some systems do, right? Some systems are big-endian and would actually print the AA first, right? That's big-endian because the most significant byte comes first. And then it would print BB and CC and DD. But most systems are little-endian, meaning it prints in the reverse order. So the first, right, so the thing that you find at the first byte of the address is the least significant byte, and that means that this system is little-endian. That's the difference between little-endian versus big-endian. You can read the section for more details and so on, but I don't think there's much more to say about this, and maybe except that it really doesn't matter, right? Like a computer, there's no trade-off here. It's not like, one thing is better at this and the other thing is better. Not really. I mean, they're almost totally equivalent. You just need to know which one is which. You kind of wish that like all computers all over the world would just kind of get on the same one thing that is probably important to reinforce, though, is that because there are these differences, if data is sent from one computer to another and you have to manage it at the level of sending bytes, then the two computers need to know which system each one is working in. So if you have one little-endian computer sending information to a big-endian computer, it's going to get a whole bunch of crazy wrong data if it doesn't know that it's supposed to be reading it in the little-endian system, that it's coming in from a little-endian system. And so in order to put that data on its own system in a way that it understands, it's going to have to reverse the endian system so that it becomes big-endian for the receiving computer, which works in big-endian. Anyway, I think that's fairly, once you understand all this stuff, that's fairly common sense, but you do need to be aware of it. You need to think about it, especially when you're thinking about computer networks, the internet, so on. When computers are sending data to each other and they don't know that much about each other, you have to be careful about that. So keep that in mind.